workshop. So we'll have two speakers. Sheng-Jie, you want to try sharing your screen?
Yeah.
It's still black for me. Oh yeah, I think it's.
Can you guys see it?
Yeah, it's on the special menu. Yeah. Okay. Good. Yeah. Okay. Great. Please go ahead.
Okay. Let me go back. Okay. Thank you, everyone. I want to thank the organizers for this wonderful workshop. I really learned a lot from these interesting talks and various interesting discussions. And thanks for having me here. Today, I'm going to talk about topological phases in quasicrystals. And because I won't have time to go into any details, so this is more like an advertisement for our paper here. So before I start, I want to thank my wonderful collaborators, Dominic Els, Abhinav Prime, and Andrei Gromov. And so let's begin. So over the past few years, there has been a great progress on understanding topological phases and topological phases with symmetries. And the early works most focus on the systems with internal symmetries. And relatively recently, we have extended our understanding to crystallized symmetries. And with crystallized symmetries, we have many more interesting phases. And there are several general approaches developed during the past few years, like the topological crystal or defect network approaches, or by the smooth state or gauging spatial symmetries. So I think right now we have a fairly good general understanding on the crystallized topological phases. However, in nature, there are also quasicrystals. So it's interesting to ask whether there are interesting topological phases in quasicrystals. And here I just show you a picture. It's a quasicrystal with A4 rotational symmetry. And because there's no translation in a quasicrystal, so you can realize some like discrete rotations that is forbidden in the usual crystal, like this A4 or 5-4 rotational symmetries. And this is actually a real space model called M. Baker tiling. You use this little square and ROMs to tile the whole space. And naively, you just look at the picture, you will say, oh, there's an A4 rotational symmetry. There are topological phases that are protected by this rotational symmetry. And that is correct, but it's not a full story. Even if you break the rotational symmetry, we show that there are still non-trivial topological phases, and that is intrinsically related to these quasi-periodic properties. And on the right, you see this is the diffraction patterns, and you will see various sharp peaks, even if there's no translation symmetries. And here, the A4 rotational symmetry is not relevant. Even if you break it, the sharp peaks is still there. So this talk is about how to understand these phases. So it turns out that you need to use a set of reciprocal lattice vectors where the number of these reciprocal lattice vectors is larger than the dimension of the space. Like you can expand the density, you do a Fourier analysis, can write the density operator in this way. And it turns out that it's useful to define this big D-dimensional periodic function. So it's like a change of variable. You define this rho delta of theta. in this way. If you write it in this way, this function is periodic in theta, in every theta. And if you restrict the theta to this form, you go back to the original density. So this means that the original physical space, you can interpret it as a section of a higher dimensional crystal, of a higher dimensional space. And this higher dimensional space is usually called superspace. And you may heard that you can view the quasicrystal as a projection from a higher dimensional crystal, and this is where it comes from. And from this, there's a very important property of quasicrystals you can learn from. So its quasicrystals have a kind of generalized symmetries, which I will call translation quasi-symmetries. And the literature is usually called quasi-periodicity. And it's a property that if you just look at the density operator and you shift the coordinates, and it's equivalent to shift, or is equivalent to a translation in a parameter space. And you can only see this property by extend the original density functions to a family of density functions parameterized by this theta. And in particular, any local operator should have these translation quasi-symmetries. And for example, if you have a family of Hamiltonians, it should satisfy these properties. So the right way to look at the quasicrystal problem is not just look at only one Hamiltonian. You have to look at a family of Hamiltonians parameterized by this theta. And for this family of Hamiltonians, you have a symmetry acting on this parameter space. Or equivalently, you can look at the ground state of this family of Hamiltonians with some symmetry action acting on this parameter space. And I will call this parameter space order parameter space in this talk. I will explain that later. And from this, you can already derive some classification principles, simply follows from these properties. But before I do that, let's discuss a more physical way to understand these phases. So our idea is to characterize these quasicrystalline topological phases by looking at quantized topological responses in the elasticity theory. So as I say, we have these many ideas. We have this order parameter space parameterized by theta. You can consider slowly varying field of theta. Like on the right, I have the two-dimensional example of theta 1 and theta 2. And this red line corresponds to some one-dimensional physical space. And you could have elastic modes that corresponds to deformations within the physical planes, or the deformation perpendicular to that physical planes. That corresponds to phonon and phazon modes. You can translate that to the deformations in this theta field. So in quasicrystal, we have more elastic modes than usual crystals. And using this for example, for 1D quasicrystals with U1 charge conservation symmetries, besides the usual kinetic energy terms, there's a topological term you can write down after you couple to the U1 gauge theory. And this is like a generalization of the, in the usual crystal. In the usual crystal, you will only have one term, because you have one theta. But in this 1D quasicrystal case, you will have many theta. So you have many these new invariants. And the meaning of this invariant is that this gives us the average charge per type of tiles. So below I show an example, which is called Fibonacci quasicrystals. It can be understood in this tile picture as a it's an arrangement of two types of tiles. I call it long tile and short tiles. And this invariance corresponds to a picture that you can bind the U1 charge to independently to these long tile and short tiles. And in this case, there are two types of tile, so you have two different invariants. So more generally, we can organize this classifications or topological terms in this compact form. And here I show an example in 2 dimensions, and the superspace dimension is 4. We have this bunch of terms. So the first term corresponds to the just usual strong SPTs that is compatible with quasicrystal symmetries. And we have 2 kinds of weak SPT phases, which I will talk about it later. And there are also these more mysterious intrinsically quasicrystal SPT phases, which is not there in the usual crystals. So how to understand these phases? So for these weak SPT phases, it's similar to the 1D case I talked about. You can consider the tiling picture. Here is the M and Baker tiling, and there are 6 independent type of tilings given on the right. If you don't consider rotational symmetry, these are all independent. So you can bind the U1 charges independently to these 6 different tiles, and this give you these 6 phases. And also you can also look at the edges. If you don't have rotational symmetries, you have 4 different edges with different orientations, and you can decorate 1-dimensional SPT phases in the dual edge. And if you do that, you get a picture on the left. So these are also the analog of weak SPT phases, the stacking of 1D SPT. And also we uncover several intrinsically quasicrystal SPT phases. The physical properties are unknowns, but we know they exist because we can write down some topological terms. For example, with time reversal symmetry, we can write down these theta terms. The theta will quantize this theta here to be 0 pi mod 2 pi. And if we don't have time reversal symmetry, there's another term you can write down. Here it shows an example in 2 dimensions. You have this WZW type action, and it's related to this higher dimensional Berry phase in this paper. And so in the paper, we also did some applications. For example, for 2D quasicrystals, for these kind of topological terms, you can derive mobility constraints for dislocations, which is shown in these equations. This B is the Burgers vector of the dislocations. K is the reciprocal lattice vector that is related to the property of quasicrystals. And this V is the dislocation velocity. And this mobility constraint depends on this SPT invariance shown in the topological terms. And we also conjecture this quasicrystal version of Lipschitz-Mattis, Oshikawa-Hastings constraints for a set of density. You can derive that. We propose a way to conjecture these constraints from these topological terms. And so finally, we also propose a general classification principle. It's called quasicrystalline equivalence principle. It says that quasicrystalline topological phases with a point group symmetry, if we only care about the classification would be the same as the topological phase with an internal symmetry, G hat, where this G hat, you can think of it as a space group of these higher dimensional crystals living in the superspace. And the quick way to see that is that if you know the abstract classification of SPT phases, I think it's first proposed by Kitaev that topological phases with internal symmetry is classified by the homotopy class of maps from the corresponding space BG to the space of ground state. And this has been extended to a family of topological phases with symmetry G, with a G action on the parameter space by Dominic and Ryan. And they propose that we should replace BG by this homotopy quotient of X. And we can apply this to our quasicrystal SPT cases. And this homotopy quotient of X is essentially the order parameter space in our case. And it's a theorem that when X is contractible, homotopy quotient of X and BG are homotopy equivalent. So that's why you have this quasicrystal equivalence principle. So, okay, here's some outlook open questions. So it's important to understand better what is the physical signatures of these quasicrystalline topological phases, especially for these intrinsically quasicrystalline SPTs. And it's interesting to study the boundary signatures and also find microscopic models and physical realizations. And it will be also interesting to study non-invertible quasicrystalline topological phases. Okay, thank you.
Thank you very much, Sheng-Jie, for a very nice talk.